Why do two pieces of metal reach across empty space and pull toward each other? No touching, no wind, no visible force at all. Something invisible is doing the work. Let's set the rules first. We're not talking about glue. We're not talking about static cling from a balloon on your hair. We're talking about a force that can lift a car, stop a compass needle cold, and keep the entire planet wrapped in an invisible shield. So what is actually happening inside a magnet? And why does it only work on certain materials, not everything you own? Let's start small. Every atom and every material contains electrons. Electrons spin. And here's the part most people never learn in school. That spin isn't just motion, it creates a tiny magnetic field, no bigger than the electron itself. Physicist Wolfgang Pauli helped establish in the 1920s that this spin is a fundamental quantum property, not a metaphor. Every single electron is, in a sense, a microscopic magnet. So if every atom has these tiny magnetic electrons, why isn't your water bottle magnetic? Why isn't your skin? Here's the twist. In most materials, electrons pair up, spinning in opposite directions. Their tiny magnetic fields cancel each other out. Total silence. No net magnetism at all. But in a handful of elements, iron, nickel, cobalt, something different happens. Extra unpaired electrons line up their spins in the same direction. Their magnetic fields don't cancel. They add together. Now zoom out. Group billions of these aligned atoms together, and you get what physicist Pierre Weiss described in 1907 as a magnetic domain, a tiny region where atoms agree to point the same way. A single domain is invisible to the eye, smaller than a grain of sand, but a chunk of iron contains millions of them. Here's where it gets interesting. In a plain iron nail, those domains point in random directions. Up, down, sideways, chaos. Their fields cancel out at the large scale, just like the paired electrons did. That's why a nail doesn't stick to your fridge on its own. So what turns ordinary iron into an actual magnet? Alignment. Force every domain to point the same direction, and suddenly their combined fields don't cancel anymore. They stack. A refrigerator magnet, a compass needle, an MRI machine, they're all just organized chaos. Billions of microscopic magnetic regions, marching in formation instead of fighting each other. But how do you actually force that alignment in the first place? In 1820, Danish physicist Hans Christian Ørsted noticed something strange during a lecture. A compass needle sitting near a live electrical wire twitched and swung, as if an invisible hand had nudged it. Moving electricity, he realized, creates a magnetic field of its own. That single observation cracked open an entirely new branch of physics. Wrap a coil of wire around a plain iron bar, run electric current through it, and the moving electrons inside the wire generate a field strong enough to force every domain in that iron bar into alignment. This is the electromagnet, and it's not a curiosity. It's the technology sitting inside your doorbell, your electric motor, and the giant scrapyard cranes that lift entire cars off the ground, using nothing but electricity and iron. Now here's the real question. Once you have that organized field, why does it reach out and grab another piece of metal? Picture the magnetic field, the way physicist James Clerk Maxwell mathematically described it in the 1860s. Invisible lines looping out of one end of the magnet and curving back into the other. These field lines aren't decoration. They carry real energy through empty space. When you bring a second magnet close, its own field lines interact with the first. Opposite poles, north meeting south, the lines connect smoothly, pulling the magnets together like two ropes being reeled in. Same poles facing each other, and the lines push back, refusing to connect, forcing the magnets apart. That's attraction and repulsion in a single mechanism. Not two separate forces, one field, behaving differently depending on orientation. But wait, why does a magnet pull a plain iron nail, which isn't magnetic at all? This is where the magic really lives. The magnet's field doesn't just pull the nail, it reorganizes it. As the magnet approaches, its field forces the nail's chaotic domains to snap into alignment, turning the nail into a temporary magnet of its own, one that's automatically oriented to attract back. The closer it gets, the stronger the pull, because more domains fall in line the deeper it enters the field. That's why a magnet's pull feels weak from a distance, and suddenly powerful right before contact. You're watching billions of atoms surrender their independence in real time. Now let's escalate. What happens when you heat that magnet up? Physicist Pierre Curie discovered that every magnetic material has a breaking point, now called the Curie temperature. For iron, that's about 770 degrees Celsius. Push past it, and thermal energy shakes the atoms so violently that their aligned domains collapse back into randomness. The magnet simply stops being a magnet. No hammer, no force, just heat, unraveling the alignment atom by atom. It's proof that magnetism isn't a fixed property of a material. It's a temporary agreement between trillions of particles, one that heat can dissolve in seconds. So if this force is happening at the atomic level everywhere around us, why does it feel so rare? Why don't more things stick together? Because true ferromagnetism, the kind strong enough to feel, only occurs in a short list of elements and their alloys. Most of the universe's atoms simply don't have the right electron structure to align this way. That's the twist most people never expect. Magnetism isn't some universal glue waiting to grab everything. It's a rare cooperative behavior, one that only a handful of elements are even capable of performing. But not every magnet is created equal. There's a huge difference between a magnet that briefly borrows its power and one that keeps it forever. Soft iron aligns easily under a nearby field, then slips right back into chaos the moment that field disappears. That's why a nail stops sticking to things the instant you pull the real magnet away. But add certain rare earth elements into the mix, particularly neodymium, and the story changes completely. Materials scientists in the early 1980s developed neodymium iron-boron alloys, whose domains lock into alignment and refuse to let go, even without any outside field pushing them. That stubborn resistance to losing alignment is called coercivity, and it's the reason a neodymium magnet the size of a coin can be strong enough to crush a finger between it and a steel surface, while a magnetized nail can barely hold up a sheet of paper. Same underlying physics, wildly different outcomes, depending on how tightly the material clings to its own alignment. Let's push it even further. What happens if you take magnetism to the extreme edges of physics? Cool certain materials down to near absolute zero, and they become superconductors, materials that carry electric current with zero resistance. In 1933, physicists Walter Meissner and Robert Oxenfeld discovered something bizarre. A magnetic field approaching a superconductor doesn't just get resisted, it gets expelled entirely, pushed completely out of the material. The result looks like magic. A small magnet placed above a cooled superconductor doesn't fall. It hovers, frozen in midair, floating on a cushion of pure repulsion. It's the same field line logic from your fridge magnet, just amplified to the point where gravity itself loses the fight. And it doesn't stop at the size of a nail. Scale this exact same mechanism up, and you get something far bigger than any magnet in your home. Deep beneath your feet, roughly 3,000 kilometers down, molten iron churns inside Earth's outer core. Geophysicists studying this planetary dynamo have shown that the movement of that liquid metal, combined with Earth's rotation, generates electric currents. And those currents generate a magnetic field. Not a small one. A field that stretches tens of thousands of kilometers into space, deflecting charged particles blasting toward us from the sun. Without it, those particles would strip away our atmosphere entirely. The same spinning electrons that stick a note to your fridge are, at planetary scale, the reason Earth still has an atmosphere at all. That's not a coincidence. It's the same physics, running at wildly different sizes. And living things have learned to read it. Researchers studying European robins have found evidence that the birds can sense Earth's magnetic field lines using a light-sensitive protein in their eyes, effectively letting them see north the way you see color. Migratory birds, sea turtles, and even some fish appear to use this same invisible field as a built-in compass, crossing entire oceans and continents by feeling a force most humans never even notice is there. It goes further still, right into modern medicine. Inside an MRI machine, doctors use magnetic fields tens of thousands of times stronger than Earth's own, strong enough to align the tiny magnetic nuclei inside your own body's atoms, just long enough to photograph your organs from the inside, without a single incision. The same underlying force that pulls two fridge magnets together is quietly mapping the inside of a human skull in hospitals right now. So let's go back to the question we started with. Why do magnets attract? It was never one simple pull. It's billions of spinning electrons agreeing to point the same direction, adding their whisper-thin magnetic fields together, until that whisper becomes a shout. It's field lines reaching across empty space, some connecting smoothly, some refusing to meet. It's atoms inside ordinary metal, getting swept up and forced into formation, the instant a magnet gets close enough to ask. It's the same invisible architecture, guiding a bird across an ocean, shielding an entire planet from the sun, and letting a doctor see inside your body without ever picking up a scalpel. Next time a magnet snaps onto your fridge, you're not just watching two objects touch. You're watching a planetary-scale phenomenon, the same one shielding Earth from the sun and mapping the inside of the human body, happening in miniature, right there in your kitchen. So maybe the real question isn't why magnets attract. Maybe it's how much of the universe around you is already quietly aligned, just waiting for something to notice.